All right, welcome to trigonometry. Sorry the semester has to start this way. I think things will get just better and better though during the semester. It won't be so long before we can meet in person, those of you who want to. I do have a number of comments and I'll wait just a minute to take roll. There might be a few people still trying to get on. This is a fairly small class. You saw my email that I sent last night, hopefully. Which means that if you just enrolled for online only, as far as I'm concerned, you can go ahead and join in person once it becomes safe to do so. We'll have plenty of room in the classroom for everybody to spread out, leave lots of room the same. I think this is an ideal size for being able to ask questions, and I've got a room that has a nice microphone built in here. What you want to do sometime during the period, hopefully, is go on WebEx. You'll see a little microphone symbol down at the bottom. And you can click the microphone on to unmute yourself and then speak and ask a question or make a comment, whatever. And then click it back off when you're done so that we don't hear your dog in the background the rest of the period or something. So my name is Dave Stapleton. Let me put my information up here. It's on your syllabus. Hopefully you got onto D2L already. I'm going to show you how to do that in case you don't know. Just look at my email. I've been here a long time. I have an office, Math and Computer Science, room 150. And if you want to call me on the phone during my office hours, you can reach me at 974-5440. Now that we've got the internet, hardly anybody ever calls me anymore. They either come in on WebEx or Zoom or send an email to me, and you're welcome to communicate by any of these things. If you communicate by email, again, this is all on the syllabus, which I'll put up in just a moment. It's dstapleton@uco.edu. All right. So things are going to get better and better during this semester. I think by the end, you'll really appreciate this class. I really love teaching this class because it's not like algebra where they say, what are we going to use this for? And you do use it, but it's hard to see that at the time. This class, a lot of the applications are immediate. We have immediate applications to things like triangulation, finding people on the earth far away. If you've got two sites and you've got somebody else lost over here, how do you find them? You can make a triangle and use trigonometry to solve it. Actually, you just have to know the angles between the detecting stations and the distances here, and you can solve this kind of problem. We can solve all sorts of wave problems that engineers use, right? You've seen those oscilloscopes where they have wave patterns for your voice and for all sorts of other noises that come out. We'll do waves, we'll do lots of triangles for all sorts of applications. We'll also do some important graphs that are used extensively in calculus and plenty of other things too. So I think you'll find it's a very nice visual and applied course. You've got my address to come on WebEx. My office hours are listed on the syllabus. Maybe I won't rewrite them here. But it's exactly the same web addresses for class. And actually, if you get on at a random time, you might see me teaching one of my other classes. So if you want to learn some calculus, you can do that. But most people need this class first to be able to take calculus. So, but if you get on the same address that you got here today during my office hours, I'll be in there for an office hour for all my classes, and you're welcome to talk to me. And then if those are inconvenient, guess what? With the internet, we can meet at lots of other times. You can often set up an appointment at another time, and I can meet you then. So anytime during the lecture, if you want to stop and ask a question or make a comment, want another example or something, get on. And this is a real good sized class for doing that. This is almost like distance tutoring, right? So any questions so far that you want to make comments on? Once we do meet in person, we're going to meet here in MCS, Math and Computer Science, room 105. That's actually where I am right now. So it'll be this classroom. And whoever wants to just stay on the internet all semester can stay on the internet all semester. I won't require you to come to class with things going on. Lots of terrible things are happening. Even if you're resilient, you can bring it home to grandma or something. And so I understand completely. My wife has asthma, and I'm very worried I'm going to give it to her if I catch it. So this is where we'll meet for those who want to come in person later in the semester. All right, well, let me put up the syllabus then now, and you can ask all sorts of questions on that, I'm sure. Let me know if you can't see or whatever. This is just the basic web page that comes up. In case you haven't been on D2L before, I think since it's the second semester, probably all of you have. But all you have to do is go up here and type in the address bar, https:// and in fact, these days you can leave that off. Just type in there learn. You can see I've had it up before, uco.edu/ if you want, and hit enter, and you'll go to the UCO website. Now, normally you need to log in. It'll ask you to log in with your campus username and password, same thing you use to get on UConnect. But like I say, since I'm already logged in, I just came directly here. Here's my page that comes up when I log into D2L. And here's my classes. So I'll click on this one. This is your class here. And you can see all these things. What you want to do once you're on learn.uco.edu, just go there and log in now if you want. Click on the content tab up here. And it will show you all the handouts I've put up. I've put out 5 handouts so far. The last one you don't need anytime soon, but the others are all immediately useful. The first one is our syllabus. There it is. Just click on this one and you can download it or you can bring it up on the screen. The second one is the geometry review. I have 2 geometry reviews here for you to look at, and you can look at both of them. I'd like you to be familiar. They're all just reviews, so you don't have to do every problem. Just make sure you're able to do every problem. Remember how to do it from high school or whenever. And then here's the Trig homework supplement. This has pretty much all the homework problems I'm going to assign all year. And then I may assign a few others, but almost all of them will be out here. So you want to download this one and print it off so you can do your homework. Looking online all the time is inconvenient, but you can do that if you want. This one is the textbook. I recommend not printing that one off. It's a lot of paper, but it's pre-calculus. So it's got lots of other material in here too. We're going to start with chapter 5 on trigonometry, but if you get stuck on anything, well, the nice thing is it goes back and does all the algebra before that. If you've forgotten some of your algebra and you do need it for this class, then you can go back and look up how to do it in the same textbook. It's a pretty good textbook, absolutely free. I give you the address on your syllabus so you can go over there and also get it from that location if you prefer not to download it from D2L. This last one, trig review formulas, I just put that up because all through the semester we're going to be getting formulas, and gradually you'll have to know all the formulas on this page. These are some of the more important ones that I want you to have memorized when you get out of class. There's also some important graphs in here. So those are the 5 supplements. You only need the first 4. Make sure you download the textbook so you can look at it. You absolutely need the trig homework supplement and the geometry review. Those are homework problems I'm going to assign, and there's your syllabus at the beginning. So I've already brought up the syllabus over here somewhere. There it is. And for the rest of the month, as I said in the email, we're just going to meet online, and then they're going to reassess, and hopefully we can meet in person beginning February 2nd, which is the first class in February. If not, then we'll just delay a little further. All semester, what I'm going to do is allow you to take your tests online as well as your class lectures online. Do make sure you come to the lectures. There are lots of things, bits and pieces you can learn here that I can't ask you in the test because it's too complicated, like proofs. But you know what happens with those proofs? What I found out, at least as a math major, was that you need that stuff later. It seems like, you know, why do I need to know this proof? It's not going to test me on it. We are going to do some proofs this semester, by the way. They're important because in lots of trigonometry applications, you have to be able to derive new identities for a particular purpose, and that means you need to be able to do the proof to do it. We're not going to spend a lot of time on proofs, but there will be some of that in here. But a lot of proofs I won't have you do because they're too long, but you still want to see it. If you take other math classes later, remembering how that works often helps you remember the formula. That's what helped me to be good at mathematics, one of the things. So come to lectures, and if you can't make it, like if you have technical problems today, I said, don't worry. All you have to do is I will upload this lecture. I may upload them all semester. We'll see if there's a need for it or not. So that you can watch it later. And so if you have problems with your sound or whatever, then watch it tomorrow or something. All right, and any questions so far then? When you come to class, you need a mask, right? And the chairs are set up to spread you out. Here's my office hours. Thursday, Mondays, and Wednesdays, I'll be at this address, same as for the class, even if nobody's there. Here's what you want to have had for background. You absolutely need to have had algebra. Here's the things we're going to focus on. Triangles, trig identities we mentioned. We're going to do complex numbers in here. That's actually important for engineers if you go into engineering. You think, why do I need complex numbers? They have imaginary parts of them, square roots of minus of negative numbers. But actually, they're really useful in electrical engineering and mechanical engineering, lots of other things, and getting at real results. So we're going to do those. And vectors. Vectors are very important in physics and lots of other sciences also. And if I know some of your majors, I may cater some of the course to that too. There's lots of people who take this for other purposes. Well, let me put this in presentation mode so I can get the whole screen up here. Let's see. It's this one. There we go. I don't know if you can see quite as well with this here or not, but here's a, actually, let's do this. Maybe it's not big enough to see. Here's some of those waves I talked about that are very important sine waves. Here's another thing we do in the class. Here's a famous photo. I've credited the author so I can use it in the song, the photographer. Someone standing out here wants to know, what's the height of this tower? Well, if you can pace off how far you are away and measure the angle up, trigonometry, you may have seen some of this in high school a little bit. They do a little bit of this in your geometry class sometimes. You can figure out the height using trigonometry. This is one of the major applications, right? Is triangles. Here's problems like two jets take off different directions and fly at certain speeds for certain hours. How far apart are they? You can do all sorts of triangle problems like that. Here's like a sound wave that makes pulses, and we'll talk about how you can generate that from sounds that don't have pulses even, and lots of other things. So those are nice examples of applications just to kind of whet your appetite. What I'll do during the semester is, at least for the first two exams, and then we'll see how the COVID thing goes afterwards. I'll grade you on a 90, 80, 70, 60 basis for ABCDs. I'll send your exams by email, and then later in the semester we'll see. I hope to be able to offer some in-person ones later. So that's put in person or by arrangement. I won't make you come and take your exams this semester. But if we can, we might make the last exam and the final in person. All right, all the dates for the exams are up here. Normally in this class, I put in lots of quizzes, but it's just too much online to do lots of quizzes. So I'm sorry that it runs the course down just a little bit. It forces people in this class who aren't used to keeping up to keep up, and that's an important part of the class. Don't get behind. Mathematics is not like history where you can just cram at the last minute to understand it. Once you get behind, your understanding gets so poor, it's like taking a basketball class and not trying to dribble till the night before the final exam and shoot. You don't learn that way. You have to practice all semester, right? Mathematics is more like that. Here's the ADA statement, which if we go in person, then you can also get facilities over at disability support and take your exams over there in a better environment. But we shouldn't have any need for this semester, since you can take them online if you want, wherever you want. The exams will be open book, open notes. which means you can use online facilities. However, no people can help you, no online tutors, none of that stuff. There is, I'll have to put it up for you. I haven't put it on the handouts yet, but there is going to be tutoring available through the math department for free. For now, they're going to have to do it online, but eventually they will offer some in-person tutoring just down the hall. Down at MCS 101, it's just down the hall and over on the other side. So 4 midterm exams and 1 final, and I'll just grade you on that. I can't, it's too difficult to do quizzes and homework over the internet. If you have to miss an exam for some reason, you're extremely ill, or your boss forces you to work at the time, I understand that kind of thing. The final exam is harder to make up, but the other exams, you just have to make them up within a week, as long as you contact me and have some sort of reasonable reason for missing it. Don't say I didn't study or I had another exam that day or something. That's not a good excuse. All right, any questions now? That finishes the syllabus, which is always a boring part of the course. All right. Well, let me take attendance here now that hopefully we're all here. Let's see, looking at your names on the screen here. Just a second here. Let's see, Michael, Tyler Michael, are you here? Maybe behind the one of my windows has popped up here. Or Leanne Calhoun.
Here.
All right, looks like everybody's here then without that. So here is, any questions on D2L also? Can you get to that and get all the downloads? What I'm going to do during the semester, I'm going to put up all sorts of practice exams and some other handouts, and you can go to D2L and download them, and that's all. Send things back and forth. Also, for your midterm exams at least, maybe not with the final, but with the midterm exams, I'll scan them and send them back to you so you can look at what you missed and try and correct it. But be able to get to this place and download the handouts that I put out there for you. All right, here's the trig homework supplement. And you notice it begins with a geometry review. There's also another one separately that I call geometry review, which has some additional problems. There, a lot of them are pretty similar. I'm going to stick mostly to this one this morning and do some problems on there. In just a second, I'm sorry with this equipment. Okay, well, then let's get started on the course. Please do ask questions as we go along. First thing we want to do is angles. Today's lecture is pretty much all review. So if you, hopefully it will come quickly. I'll go faster than I would otherwise. When you have two rays emanating from a point, we say an angle is formed between them. If you move counterclockwise, we say it's positive measure. If you move clockwise, we say it's negative measure. All right. Now, how do we measure an angle? We'll say this. By the way, a ray is a half line is what it is. It starts from a point and goes out forever in one direction. Measuring angles work like this. We'll say that here's an XY coordinate plane. When we go all the way around, that'll be a measure of 360 degrees. All right. And if we go halfway around and we're measuring equal increments, then it follows we should have halfway around is 180 degrees. We'll call this a straight angle. We'll call 360 degrees one rotation. Then if we go half of the straight angle, just from the x-axis to the y-axis, we'll call this a right angle. Then there are lots of important angles that come up in construction and in nature and lots of other places. For instance, if you take half of a right angle, we'll call this a, well, let's see. If this is 360 degrees and this is 180 degrees, this is half of that one, it must be 90 degrees. And this one being half of that one, we'll say is 45 degrees. So this will be special angles. We also want to take 1/3 of a right angle. If we break the first quadrant here, right? Remember from geometry, you can break the XY coordinate plane into 4 quadrants. I should put those down here too. Where X and Y are both positive, we call that quadrant 1 and we give it a Roman numeral 1. This is all review terminology, so we don't get confused all semester. Quadrant 2 moving counterclockwise for positive, right? Quadrant 3 over here where X and Y are both negative and continuing to move counterclockwise. Quadrant 4. These mean, right, 1, 2, 3, but V is 5 and you put 1 on the left, it means 5 take away 1, it's 4. Quadrant 4 Roman numeral there. And we'll use those quadrants all semester. And we'll say if we break it into thirds, then this angle here of 1/3 will be, well, 1/3 of 90 degrees is 30 degrees. And then 2/3 of a right angle will be 60 degrees. And those will be our special angles. They come up a lot in triangles, for instance. I'm not getting any questions yet. Maybe that's because it's easy. But if you have questions, please ask. That's got to be part of the purpose of this class rather than just watching a video online. Right? So those are our special angles that we're most interested in. Now, there are 3 major theorems that we're going to use all semester that come out of your previous history with geometry, right? Because what happens in trigonometry is we're about solving triangles for one big topic. Often a nice trigonometry formula gets us started, but then for the last part, you'll find it's easier just to go back to one of these 3 theorems and do it this way instead of using more trigonometry. You can do it with trigonometry with a lot of work, but why do a lot of work when you have one of these easy theorems? Here's the first one, just out of geometry. We won't prove these since they're review, but we'll just say the sum, you absolutely have to know these, of the angles, all of the angles in any triangle is 180 degrees. At least in Euclidean geometry. There are exotic geometries also where That's not true. And then we have these kind of examples. Suppose I have this triangle here, and I tell you that this is 100 degrees, and this is 53 degrees. 53 degrees. What is angle alpha? I will usually use Greek letters for angles. That's just convention. You don't have to do that. But you can have these kind of problems, right? Find alpha. There's no sense in using a lot of complicated trigonometry. Just use the sum of angles theorem. And you say if these add up to 180, then alpha must be 180 less the other angle, right? Subtract 153 degrees, and that leaves you 37 degrees. Oops, 27 degrees. There we go. Then we'll say this, two angles are complementary if their sum is 180 degrees, right? Excuse me, 90 degrees. I put the wrong one first. 90 degrees. Or supplementary if their sum is 180 degrees. It's waking you up there. All right, so we can have this kind of thing. Here's another example. Find beta in this situation. Here's a straight line. Here's an angle of 127 degrees, and here's beta. What's beta? Well, these two angles add up to a straight angle, 180 degrees. So we're going to say beta must be 180 minus 127 is 53 degrees. So there's supplementary angles, this one and this one, because they add up to 180, a straight angle. Now that triangle formula that the angles add up to 180 degrees leads to a nice consequence for right triangles, which are of special use to us. We're going to spend quite a lot of the first part of the semester solving right triangles. Maybe some of you have done that before. We won't spend too long on it. But a right triangle is a triangle that has a right angle. It is a 90-degree angle, right? Can't have more than one, because if it had two of them and already add up to 180 degrees, there wouldn't be anything left for the third angle, right? So that's a right triangle. An angle, a triangle with a right or 90-degree angle in it. For these, the acute angles, and what an acute angle is, I'm trying to introduce this notation all as we go along, because otherwise if I start off saying this, I'll probably befuddle you before we get started, right? What's an acute angle? It's an angle that's less than 90 degrees, right? Between 0 and 90. An acute angle, the acute angles in a right triangle always sum to 90 degrees. They're complementary angles. It's obvious why. But this will just save you a step at every problem. More down the line where we're solving right triangles, we have one angle left. Here's an example. Suppose I have a right triangle, a right angle, I'll mark with this little corner symbol here. That indicates it's 90 degrees. Now, if I call this one 42 degrees, I measured almost half of a right angle, let's say. Then what's this one that's left? It's not drawing real accurate. Suppose here's beta. What is beta? What you know is since the sum of the three angles is 180 and 90 of it is right here, the two that are left sum up to 90. That's what I'm saying here. The two that are left, these two acute angles in a right triangle that are less than 90, will always add up to 90. So you simply say beta is 90 minus the other angle in a right triangle. So I've got 48 degrees left. So there's supplementary angles, when two angles add up to a straight angle, and complementary angles that occur in right triangles.
You can see the bottom part of the board.
One of the great theorems. This has a really easy, elegant proof that I always like to do, but I'll probably bore you if I do it, so let's not. Let's put theorem 2. But you can do this at home pretty easily, actually. It's kind of neat. Goes back to Pythagoras, so it's called the Pythagorean theorem. We're going to need this all semester. Sometimes people try and apply this to any triangle, but unlike the last theorem, the sum of angles theorem, it doesn't apply to any triangle. It only applies to right triangles. And it says this, a right triangle with legs AB and hypotenuse C. These are standard letters people like to use in textbooks, so it's good to get used to these letters, but you don't have to use these, obviously. Has always that C squared equals A squared plus B squared, and here's the picture. A right triangle. The two sides that are not opposite the right angle are called legs. So I could put in here not opposite the right angle. That's what a leg is. And the hypotenuse is the one that is opposite the right angle. Right? Opposes it. This is always the longest side because of this theorem, right? So when I give you a triangle here, it's a right triangle. Given two sides, you can always find the other side, right? Well, that's what the homework is for today. It's just to go back and review. I'm not going to ask you to turn in the homework. The homework is all just to practice for the exams. What I'm instead going to do is make the exams like the homework problems, but I'll change them around a little. And I'll give some slightly different applied problems sometimes too. No questions so far? I'm going to start doing some more difficult problems as we go along. This won't be difficult yet. Suppose I say find the length of the missing side. I'll just say find the missing side length. Suppose I gave you this right triangle, kind of a famous one. Can't draw it though. Suppose this side is 5 and this side is 12, and I don't know what the hypotenuse is. All right, well, I use this theorem, and I want to point out that what we really want for the semester, because this comes up so often, is not this theorem directly, but I'm putting this up today so you won't be confused all the semester when I do it. But this one solved for each of the sides. Since the square of c is this, c must be the square root of this. So c is always square root of a squared plus b squared is how I can find the hypotenuse when the other two legs are known, right? So I'll simply say here, by the note, I'll call it the Pythagorean theorem solved for c. C is the square root of 5 squared plus 12 squared here, is the square root of 25 plus 144, is the square root of 169, is 13, right? So this triangle actually has integer sides. Integers are numbers that have nothing after the decimal point, by the way, including the negative numbers and 0. We have integers, 5, 12, and 13. And that's actually uncommon. Most of the triangles, we won't get such nice results. When you do get all integers for the side lengths, then we say those three numbers are a Pythagorean triple. There's an interesting story behind this too. We can talk about sometime. All right. There's an infinite number of those. You can look it up online. It's kind of fun to Google these things. There's an infinite number of triangles with integer sides, but almost any triangle you draw still is not going to have integer side lengths. So this is a 5, 12, 13 triangle. You've probably seen this famous one here, right? 3, 4, 5, right triangle. We'll see that during the semester too. Has integer side lengths, but most of them will not be so lucky. All right, that was one note. C is square root of a squared plus b squared. But what if I want to solve for one of the other side lengths? If I rewrite this as a squared equals c squared minus b squared and square root it. So I first write a squared equals c squared minus b squared. Then I can square root this one and say a is the square root of c squared minus b squared. So if I want to solve for the leg a, then I just put a minus in here instead of a plus. And similar, if I solve for b, I get b is the square root of c squared minus a squared. Here is the Pythagorean theorem solved for each of the sides. And this is what I'm going to put up all semester. Don't get confused. It's just the Pythagorean theorem. It's really easy, right? So let's try another one where we have this. I'm going to tell a few stories as I go. I think it makes the course more memorable. And also, if you know this kind of thing, might help you if you decide sometime to become a math major. I enrolled as an economics major when I was an undergraduate. Found at the end of the first year I was doing well at math and I liked it, so I switched to become a math major. So maybe I'll convince you if you like some of these things. What I found out was amazing is that you can go into a whole lot of different fields with mathematics. I've worked at the FAA, for instance, for a number of years part-time. I used to work at Vandenberg Air Force Base as a flight analyst out there as a contractor to the Air Force. I worked at Edwards Air Force Base in California. So aerospace engineering is a big application. Physics is a big application. Engineering. Mathematics has lots of applications in for theorists and even business economics and so forth, right? And so there's lots of other fields that this will apply to. Maybe you'll get some inspiration out of some of this for those things. Here's another problem. Here's problem B. Suppose I have this kind of triangle, not so lucky. Suppose this one is length 5, and this one is length 2, and it's a right triangle. What is the length of B? All right, well, I use the Pythagorean theorem solved for a leg, and it's square root of the hypotenuse squared minus the other leg squared. So it's 25 minus 4. It's the square root of 21. On the test, I want you to leave it like this. It is true you can run the decimal in your calculator, but this is an exact answer. One interesting thing about mathematics, here's one of the things I said you'd pick up during the course if you come to the lectures that you don't, I'm not going to ask you on the test, right? Is if you get a square root of any whole numbers are the integers that aren't negative, 0, 1, 2, 3, 4, 5. Square root of any whole number, it's always either another whole number or it goes on forever without a repeating pattern, which means it can't be written as a fraction. All fractions have a repeating pattern, including the possibility they terminate, right? Like 3/5 is 0.6. If you put 3/7, it repeats 7 digits over and over ad infinitum. And it's a repeating decimal, but this one goes on forever without a repeating pattern like pi. We call it an irrational number. And so we leave it like that because no matter how good your calculator is, it can't put enough decimals to reflect a repeating pattern. So there's just, this is good. If somebody needs to send a mission to Mars, they can get as many decimals as they need on the right machine. But if they just need to go across the street and they're measuring a triangle, then they don't need so many decimals. And this allows arbitrary decimals on your calculator. By the way, I meant to mention, any calculator that has trig functions is fine. How do you tell? Almost all of them do, unless you buy a $5 calculator. But a lot of these $10 calculators you get at the store have trig functions. I know you can't see this very well. This is an old style TI-84. This is plenty good for the class. I recommend a calculator with graphing capability. So I'll have a big screen up here if it's got graphing. You don't have to have graphing for this course. All the graphs can be done by hand. We will have graphing. But if you have this, you can kind of check your answers on here. So get a graphing calculator. You can buy these for $30 brand new at Walmart. And you don't have to buy this TI-84. I like these because I have a demonstration pack for the classroom, but this semester won't matter. But sometimes I do calculator demonstrations. I don't know if we can online or not. One of the things we may lose. But I just turn this on. I can put in square root 21 and get anything I want. Here's how you tell if it has trig functions. Look for the button that says SIN and COS. These stand for sine and cosine, two trigonometric functions. If you see these two buttons on the calculator, then it does trigonometry. Usually the package will tell you anyway, but look for a calculator that does that. Like I say, you can buy that for $10. And if you spend about $30, you get a nice Sharp or Casio. They're a lot less expensive than these TI calculators, and they do just as much. You get a nice color graphics graphing calculator, and then you can do these things as far as you want with as many decimals as you want. Any questions yet? I turned the volume all the way up, actually, in case somebody was asking a question. I don't want to talk to the walls all the time, so ask questions. All right. So there's the Pythagorean theorem. And like I say, in most triangles, when we're given two sides, the third side will not be a nice integer. Here's some harder problems. I said I'd do some other problems to try and give you a workout on these. I'm looking on the geometry review that's at the beginning of the UCO trig supplement, not the geometry review that's by itself. And it has this one. I'm going to do a bunch of review problems of what we've just been doing here. Suppose I have this picture. I have a right angle, maybe these are the X and Y axes, and I have a line segment going like this, and this angle is some measure X plus 4. I didn't use Greek letters this time, that's fine. And suppose this one measures 3X plus 4. And I say, find the measure of these two angles. Or I'll just say, find these angles. What are they? Now it's a little harder, right? But what you do is you notice, since they add up to a right angle, right, they're complementary. They add up to 90 degrees. So we'll write down immediately 3x plus 4, the first angle, plus x plus 4, the second angle, must add up to 90 degrees. I'm sure this is on screen. I sometimes forget them right off the screen, so you might have to tell me sometimes. When I'm going too far over. Let's see. So I write this for that triangle. And now it's just an algebra problem. So I told you you need algebra. You need to be very good at factoring and simplifying square roots and that kind of thing from algebra. We'll talk about that a little bit as we go here. If I have this easy algebra equation, I just combine like terms and say 3x plus x is 4x. 4 plus 4 is 8 equals 90. So you combine your like terms. Well, I need to this should have had degrees on it. We should fix that on the handout. We'll combine the like terms here again and say 4x equals 82 degrees by subtracting 8 from each side, right? Now we divide this by 4, and we have x is 82 over 4, which is 20.5 degrees, right? These are okay not to leave as an exact number because this is a terminating decimal. But what I usually like better is to write 41 halves on this, right? 41 halves is an exact fraction. When that fraction does not repeat on forever, then it's okay to leave it as a decimal form because I can see that this is exact. But if you have something like 3/7 that repeats, I want you to leave it as a fraction and not write the decimal form because the decimal form is hard to figure out what fraction it came from. It's hard to tell what the exact number was. All right, so either of these I'll accept in this case because it's a terminating decimal. But I like the fractions for most applications. So there's how to solve a slightly more difficult one. All right, now we talked about two of the theorems. We said one of them is the sum of angles theorem, another one is the Pythagorean theorem. What is another theorem that's very important to us this semester? That's for similar triangles. This will save us a whole lot of work. And actually, trigonometry is built about this principle for right triangles. Two triangles are similar if they have the same three angles. And actually, if they have two the same, then by the sum of angles theorem, they have to have the third one the same also. So if you see two the same, you know immediately they're similar. But the definition will be they have the same three angle measures. All right, so something like this. Here's alpha, beta, and gamma. I better draw bigger. Alpha, beta. You can put these anywhere you want. But here's the convention. Opposite alpha, we normally put A. Opposite beta, we normally put B. And opposite gamma, we normally put C. There's another convention for labeling these. We can also call this point A and say this is angle A with a capital letter. Say this is point B and label it with a capital B. And this is point C, label it with a capital C. So capital letters can label angles if you want. That's another common thing in textbooks. I'm going to stick to the former convention, use Greek letters, alpha, beta, gamma. Gamma is not even the third letter, but we still use it. And put them opposite these respective side lengths A, B, C. So here's a triangle. Here's another triangle. It looks the same shape because it has the same three angles, alpha, beta, and gamma. But it's a bigger size. We just scale everything up. What happens in similar triangles is that the side lengths all have the same ratios. If this one's twice as long as this one, then also this one will be twice as long as this one, and this one twice as long as this one. So just for, you'll see why I don't want to use the capital A, B, C for angles. For this bigger triangle, I'll use capital A opposite alpha, capital B opposite beta, capital C opposite gamma. And here's the theorem for similar triangles. That big C is to little c. It's a scaling factor, like 2 to 1 or 3 to 1 or whatever it is. It has the same scaling factor as big B is to little b. It's the same factor is big A is the little a. All right? So that will be the similar triangles theorem. Well, there's actually another one. That's one similar triangle result. By the way, I haven't been doing it so far, but I should do it. You should put a star on the Pythagorean theorem and a star on the sum of angles theorem. These are actually put a star on the Pythagorean theorem, solve for each of the sides. Put a star on this similar triangles theorem and put a star on the sum of angles theorem. I'll do that when I want to memorize things frequently. There's another way you can do this though also. You can also take the ratio of sides of corresponding triangles. If these are opposite the same angle, we'll say big A is to little a as big B is to little b. Oops, I didn't write that right. I'm sorry, two in the same triangle. Big A is a big B as little a is to little b. And big A is to big C as little a is to little c. And big B is to big C, and little b is to little c. So this is also a similar triangles theorem, and you can use either one of those whenever you want, and it will save you lots of steps of complicated trigonometry throughout the course. With that in mind, let's try some problems there. You will find as the course goes on, too, that you'll improve your algebra and geometry skills a little by reviewing these things and applying them. I always found when I took a course that applied things, I remember the previous course a whole lot better. So once I took calculus, I was very good at trigonometry. And once I took calculus 2, I was very good at calculus 1 and so forth. This course usually makes you good at algebra and geometry, for instance. Then come back to the handout here. Here's a nice applied problem for this one. We're starting to get a little more complicated. This is not necessarily a right triangle, so we can't apply the Pythagorean theorem. The Pythagorean theorem only applies to right triangles. One of the big mistakes people make during the semester trying to apply it to triangles that are not right triangles. So suppose this is D, E, B, A, C. And suppose this side measures 15. This side, we don't know what it is, we'll call it X. This side length is 11. This side length is 7. Given that AB, this means the line segment from between A and B, is parallel, this means parallel to the line segment between D and E. Find X is the problem here. Wonder how long this little segment is. How can we find that? We can do that actually with similar triangles, right? There's a number of ways to do this. You don't have to do it exactly the way I do, but the idea is to do one of those starred formulas there that includes X. So I could say, well, this angle is the same in both triangles, right? Because it's the same two rays coming out, right? Now, since these are parallel lines, we have this nice theorem from geometry, maybe you recall. Whenever you have parallel lines and you cut it with another line, you call this a transversal. I may use that term during the course. It just means it's cutting two parallel lines. These two angles are equal, right? Those are alternate interior angles. Also, these two angles are equal, right? These are it's usually called opposite angles. There's another term. Anyway, so these two angles will be equal and the alternate interior angles will be equal. And this one and this one, well, because these opposite angles are equal, this one must be congruent, having the same measure, to this one. And all these equal, so this one is actually equal to this one now, right? These are obvious, maybe, but this one is actually congruent to this one because they meet, right, the same way. But these alternate exterior angles are also congruent. So you have all those congruents, and then this one is supplementary to this one. So it's this one might taken from 180 is congruent to this one, is congruent to this one, and this one. And you have these kind of nice properties. We can apply those kinds of things here and say, well, if these are parallel, then this angle must be congruent to this angle. We'll put the same number of hash marks on each of these. Well, wait a minute, if these two triangles have two of the same angles congruent, then the third angle must be congruent also, right? Because the three angles add up to 180 degrees, they must have the same amount left. So this one must be congruent to this one. That makes these similar triangles, right? When these two are parallel and they share a common angle here. So with that idea in mind, now I can try and find x. And let's say that this side in length is to this side, comparing corresponding sides of the similar triangles. X plus 15, the long side of the big triangle, is to the bottom side of the big triangle, is to the bottom side of the little triangle, 15, as, well, we just need to put two other corresponding ratios. We know these. Big triangle, little triangle here is 11 to 7, right? So here's a similar triangle thing by our last equation for similar triangles here. Now all we have to do is apply algebra to solve that for x, right? So we multiply both sides by 15, and then we'll cancel the 15 on the left, getting x plus 15 equals 15 times the right. You absolutely have to remember your algebra here. If I have a whole number times a fraction, right, what I do is I just write that as 15 over 1 in this case, and multiply top times top over bottom times bottom is how you multiply fractions. So this is 11 times 15 over 7 times 1 is just 7. And I don't yet multiply it out because what happens is sometimes some things cancel. What I want to do is always, I want you to reduce your fractions. If something cancels on the top and bottom, I want to do it, right? So remember, this is fundamental theorem of algebra, actually, every integer greater than or equal to 1, well, greater than or equal to 2, factors uniquely into the product of prime numbers, numbers that are only divisible by 1 in themselves, up to just reordering those factors. So this actually factors, 11 can't be written as a product of any two numbers. It isn't divisible by any two numbers except 1 in itself, so it's a problem. So is 7, but 15 factors is 3 times 5, and if you think of these factors, 11 times 3 times 5, then you can see if anything cancels, and nothing cancels. I can't cancel 11, I can't cancel a 3, I can't cancel a 5. So there's nothing to do. This is already reduced. Now I'll multiply it out. 11 times 15 is 165, and the answer is 165 over 7. On the test, yeah. If I ask you for an exact answer, then leave it as a fraction. This particular problem says round to 2 decimal places, however. Yeah. So I'm going to run this on the calculator. 165 divided by 7. And I get 23.5714 ... Rounding, I'll call that 23.57. The rule for rounding, just to remind you, is if I say round to 2 decimal places, that means 2 digits past the decimal point. The digits are these numbers 0 through 9. 2 digits I take past the decimal point, and then if the next digit is 5 or greater in its exact representation, then I round up and call it 0.58. But if the next digit is 4 or less, as in this case, then I just leave it as the last digit alone. So I call this approximately 23.57. You just write equals. The squiggly sign means approximately equal to. But there it is, rounded to 2 decimal places. All right. Can everybody see that okay? Yes. Yeah. So there's rounding also. See how many old topics we need to pick up if you're rusty on your math. A lot of people have to take a math class, wait till they're graduating seniors. Maybe some of you are those. they haven't had math in 4 years since high school, so sometimes I need to review this. But this is hopefully to save us a lot of trouble later we do this review. Next time we'll start formal trigonometry. I think it'll be probably more interesting. I'm sorry if this is a little boring today for some of you. All right, so there is that problem worked out. These have nice applications in other ways too. Here's another example. This one is a personal example actually, and it's similar to the problem on the other geometry review. I had a tree, a beautiful pine tree in my backyard, really tall, and the mountain pine beetle came and got in it and killed it. And I had to cut it down. It was so tall. I thought, boy, I'm worried about cutting this thing down. Maybe I get somebody in to cut it. But they said, well, how tall is it? I don't know how much to tell you it's going to cost, but I don't know how tall it is. So I had to figure out how tall it was. And I didn't need trigonometry, even though we said from that castle problem, you can figure out with trigonometry. Can you guess how I did it? Here's my tree. You can do it with similar triangles. If the ground is flat, like this, is what we'll assume unless we say otherwise, and maybe the sun is out here shining, it makes a shadow for the tree, right? Here's the tree's shadow out to this point. What I need to do then, in order to figure the height of the tree, is I can go stand out here, right? And I'm just about exactly 6 feet tall. So I'll call this side length 6, and then I'll measure off this distance along the ground. Suppose this was 9 feet, right? Is my shadow at some particular time of day. And now I can also, from the tip of the triangle out to this point, pace off on the ground the distance to the tree from the tip of the tree's shadow back to its base. And suppose that this is 36 feet. Well, what's the height of the tree h? Right? So here's an applied problem. Find h, given that this is 6, this is 9, and this is 36. Once again, we have two similar triangles. In this case, they're right triangles, right? They have this. They both have a right angle here, right? Because the ground is level. So that's one angle the same. Then they share this common angle here. So two angles are the same. That means all three are the same. They're similar. I can now write, for instance, that 6 is to 9, my height to my shadow's height, as h is to 36. Right? Now it's just a matter of multiplying by 36. H must be 36 times 6/9. Well, 36 is 36 over 1. I take top times top over bottom times bottom. I get 216 over 9 is my height, and I don't want to see that answer on the test. Why not? There's another thing you pick up by coming to class. How do you know if this number has a common factor with this one? Well, this one's factoring is easy, right? 3 times 3. By the way, if you buy a more expensive calculator, you'll get one that can factor and can reduce these fractions for you. You're welcome to do that. When we're taking exams at home anyway, I can't hardly watch that kind of thing, and neither can if I get locked down browser or something. I can't even watch that. But any calculator you want is acceptable for the tests. And you can get one that reduces these fractions for you, but you need to know this just for yourself. 9 is obviously 3 times 3. Is this one divisible by 3 so I can cancel one of these? Right? Well, here's how you can tell if the sum of the digits is divisible by 3, then the number is divisible by 3. There's coming to class, I was telling you. 6 plus 2 plus 1 is 9 is a multiple of 3, so 216 is also a multiple of 3. If I figure it out, let's see, it's 72 times 3. So I'll write now that h is 72 times 3 over 3 times 3, and I can cancel a 3. Well, wait a minute, 72, 7 plus 2 is 9, is divisible by 3. It's also divisible by 3, right? So let's see. Must be 24 times 3, right? And so I can cancel these 3's. The tree is actually 24 feet high, right? So now I can call the contractor, and I found out it was gonna be $600. I wound up, I don't know if this is the exact height I had, but it's pretty tall. And wound up buying a chainsaw and saving a lot of money myself besides. All right, so there's some applied problems using these three principles. Now there's some special triangles that we want to talk about today too. Maybe we should call this a fourth theorem. I said there's four theorems, but these are derived from the other ones. So. Special triangles are angles that have one of those three special angles in it, 30 degrees, 45 degrees, or 60 degrees. And then any multiples of those we'll also call special angles this semester. We'll mention that again as we go. So, but special triangles will have one of these three, one of these angles or a multiple of it in it. Here's the important ones for us. Actually, now let's give this one. Here's an equilateral triangle. 60 degrees, 60 degrees, 60 degrees. If all angles are equal, then 3 times that angle must be 180, so each angle has to be 60. We call this an equilateral triangle. There's also triangles with two sides the same, alpha and alpha, and this could be some other angle, beta. We'll call that an isosceles triangle. But then we can apply some of these things to solve some special right triangles. Those are the important ones. Suppose I gave you, for instance, let me put this back on the other side of the board. A triangle like this, where it's an isosceles right triangle, and 45 degrees, 45 degrees. What is the remaining side for this one? Well, you can apply the Pythagorean theorem to this, right? The hypotenuse C, if you like, is the square root of this squared plus this squared. A squared plus A squared is the square root of 2A squared. And remember, the square root of the product of non-negative numbers is the product of the square root. So it's square root of 2 times square root of A squared. Square root of A squared is just A, so this is square root of 2A. This side is always just square root of 2 times as long as this side. This really threw the ancient Greeks for a loop because they didn't have decimal numbers, they just had fractions. And an interesting result is if you take a triangle like that, like 1, 1, square root 2 is a special case of a 45, 45, 90 triangle. Every 45, 45, 90 triangle, you just scale all three of these sides by A, whatever number you want, and whatever positive number you want, and you get another 45, 45, 90 triangle similar to it. But the thing about this one is square root 2 cannot be written as a fraction, m over n. You can show it as a non-repeating decimal. Consequently, they couldn't write a number for the length of this side, if the ancient Greeks couldn't, because it wasn't a fraction. They didn't have decimal numbers to go on forever. So kind of an interesting story there. That's the motivation for doing decimal numbers instead of just fractions, actually. All right, so if you're going into teaching school or something, maybe that'll be an interesting fact for you. All right, so here's this one. Every 45, 45, 90 triangle is what we call these, right triangles, has side lengths a square root 2a, always. So you can try and solve those given one side, you can solve the whole thing. The other one, the other problem Here's a 30, 60, 90 triangle, right? If I put a 60-degree angle here and a 90 here, that leaves only 30 degrees for the last one. So there's a triangle. Now, if I make this one A, what are the other sides here? Well, here's what you can do. Draw another one of these with equal lengths. Let's flip it over and make another one. And now 60, 60, because it's an equivalent triangle, and 30 makes this a equilateral triangle, 60, 60, 60. So if this is A and it's half the base, then this is A. Every side length is now 2A. So this side of a 30, 60, 90 is actually twice this one. I'm doing a proof here, but I won't ask you this proof. I told you proofs will help you remember this, right? And then what's the last side, right? If this is A and this is 2A, remember to find the last leg, B, if you like. It's the square root of the hypotenuse squared minus the leg squared. Now it's starting to get more complicated, right? Well, this is just square root of, when you square numbers, you take this one squared times this one squared. It's 2 squared times A squared is 4A squared. Minus A squared. It's square root of 3A squared. Product of square root of the product is the product of the square root. So this is square root 3A. Now we have the theorem for the other triangle. We memorized this one. A square root 2A. And we also memorized this one for the other special case. These come up, like I said, in nature and construction quite a lot. If you have a 30, 60, 90 triangle, I forgot to draw the angles in here. So this one's called a 30, 60, 90 triangle. The side lengths are always A square root 3A and 2A. Memorize those two triangles because those will come up a lot this semester. They're very useful in lots of applications. I need to watch my time. That's why I'm rushing just a little here. So I want to solve a problem that's like that. Find it. I think it's on the other sheet. I didn't look that up. Let me just write this one down. Suppose I'm given this triangle here, and I tell you that this is 5 units long, and it's a 30, 60, 90 triangle. Find X and Y. How can I find those? All right. It's a little tricky here. I'm giving you kind of a hard one at first because I don't have time for enough of these today. But you remember from this picture here, can you see this all right? That if this is X, this is always square root of 3X, right? A and square root of 3A. So I have square root 3X is equal to 5. It must be that X equals 5 over square root 3. There it is. There's X. Now what's this one? If this is A, this is 2A. So Y must be 2X. Right? So Y is easy. Y is just 2X. Let's do that next. I'm sorry. So this is actually a good answer, and a lot of mathematicians will leave it like this, but your algebra teacher would say, oh, you've got to rationalize the denominator, right? So what you do, that means get the radical signs out of the denominator. Multiply top and bottom by square root 3. So at the bottom is now 3, right? And we'll actually call this 5 square root 3 over 3. On the test, I'm okay with leaving it this way, but if you want to compare it with the answer in the back of the homework, on a homework problem, you need to rationalize it because those will all be rationalized. Textbooks do that too. So here's the answer that will be back in the back of the answer pages. There's X and Y, or there's X, and now Y is always equal to 2X. It must just be 10 square root 3 over 3. There's the other two sides of this triangle. So there's a nice review of geometry. I hope that'll help you throughout the semester. Next time, we'll get into trigonometry, using this concept of similar triangles, actually. In the meantime, let me just run one thing over here. Never got around to the classroom rules. Let's see. Oh, I know where it is. I do have a few classroom rules just to leave you with. This on here okay? Yeah. If anything can go wrong, it will go wrong. That's Murphy's first law. So always expect that. All right. When you do your proofs, this is what always happens. The errors are the first step. So when you find a mistake, that's where it is. All right. When you come up with a new theorem, if true, it's not new. If it's new, it's not true. All right. That's the way your theorems always come out in this class. Exams, you'll always catch on after the test, after you made the mistake. Final exam, everybody forgets to put their calculator in radians mode and misses every problem. Homework, your dog eats it. So here's also, this is really true in mathematics. Every time you answer a new theorem, there's always two new questions for the one you answered. And what you find in politics, I bet you watched it this season, right? With all the debates back and forth. If you do enough research, it will tend to support your theory. Anyway, so hope that gets you off to a good start. And Murphy's law, Murphy was actually an aerospace engineer. This is named after. This concept didn't start with him, but Murphy's last law was that Murphy was an optimist, right? So we'll have some things go wrong, but we'll get it all worked out. I hope you find this a really interesting class with lots of applications you can already see. I'll put this up online if you want to see the lecture again. And otherwise, I'll see you next time. Come by my office hours and talk to me. I'd love to get to meet you in person online. Thank you. Any questions?